Hello everyone, my name is Ashley Goodnight and this is my Reading Week 9 video. This week, we expanded our understanding of the fundamental concept of energy. We delved deeper into the idea of potential energy, specifically the new case of spring potential energy. Note that we use spring potential energy for more than just springs. We can also visualize ropes as chains of springs together. We can derive an expression for spring potential energy looking at it as the work done by a spring. Following these derivations, we end up with the spring potential energy equation as half k, the spring constant, times the displacement x squared. This week, we also built off the concept of energy graphs. In the case of springs, we know that the displacement x is negative in cases of compression, while x is positive in cases of stretching. However, for spring energy, since the displacement is squared, the potential energy is always positive. Therefore, the total energy is always positive. Let's imagine a simple spring system that only involves kinetic energy and spring potential energy. The energy graph would look like this. We also explored how to model the motion of a spring mass system analytically. Starting with Newton's second law, we end up with delta V divided by delta T equals the negative spring constant times the displacement divided by the mass as delta T approaches zero. This can be rewritten as dV over dt equals negative kx divided by m. We can simplify this further, knowing that the velocity equals dx over dt. To be honest, this is where the steps got a little bit confusing. We end up with the function x sub t equals a cosine omega t, where a is the amplitude or maximum stretch, while omega equals the square root of k divided by m. In order to clear up any misconceptions, I went to Khan Academy. Google kindly directed me to an article on simple harmonic motion in spring mass systems. On the topic of clearing up misconceptions, I reviewed and refreshed my past knowledge on two energy concepts. The first is path independence, which means that the work done in moving along a path in space depends only on the initial and final endpoints of the path. This idea of path independence applies to potential energy. The other concept I knew vaguely was dissipation. We say a force is dissipative if it reduces the kinetic energy and never gives it back. I think about it as an irreversible loss of energy from the system. Examples include friction and drag forces. We are all familiar with the conservation of energy theorem, so how do we lose energy? Well, the energy isn't technically destroyed, it's lost when it's converted to thermal energy. This week's videos apply directly to my major of electrical engineering. Georgia Tech allows EE majors to pursue the thread Electrical Energy Systems, a branch of electrical engineering that explores power systems, power electronics, and electrical machines. This EE thread explores different methods and approaches to transforming energy into electrical energy. This energy transformation cannot take years or centuries. It needs to happen in a timely process. This is where power comes in. Power, as we learned, is the amount of energy change in a given amount of time. With that, I am concluding my presentation. Thank you everyone for listening. See you all next week.